Hello and welcome. My name is Simon, and we are Team AutoSail. AutoSail was part of the final year autumn project for the robotics, dependable system, and embedded system students. This will be the final presentation of the project, and the members of the project can be seen on screen right now. On the next page, I will talk about the agenda, and the presenters will be introduced. Next slide. Yeah, thank you. This is the agenda for today's presentation. I will talk about the project background and the project goals. Johan will talk about the requirements, system model, safety, quality, and validation and verification. Emma will talk about the hardware implementation. Casper will talk about the path planner in the software implementation, and Patrick will talk about communication, simulation, and vision in the software implementation, and then the results, discussion, and questions. So, sea vessels have historically been an important means of transportation throughout all of the world. This is especially true for sailboats. By utilizing the wind to traverse open water, an efficient means of travel is created. To utilize wind as a means of propulsion, the sails on a sailboat are controlled during operation to manage direction and velocity of the vessel. This is performed by personnel manually. Due to the limited effect of propulsion from wind and the required personnel, sailboats have been replaced by more modern types of travel for larger transportation and shipping. And in modern society, sailboats are mostly used for recreational use due to the limited usage in comparison to tankers and cargo ships. But sailboats have gained more attention in recent times due to the possibility of environmentally friendly travel. With the addition of wind power and solar energy in the form of solar cells, an evolution is possible for sailboats to accommodate the necessities in addition to propulsion. Furthermore, the evolution of artificial intelligence enables sailing vessels without the need for sailing personnel in the same scale as before. The offshore industry and sea freight are today operations with a high risk of labor and a high environmental impact. This requires intelligent systems, and with environmentally friendly autonomous vessels, such as our boat, Norrsken, the industry can set course for a more sustainable future. The World Robotic Sailing Championship is a competition, is the largest competition in the world for fully autonomous sailing boats. The competition is open to wind-powered unmanned surface vehicles up to 4 meters long. The conference provides researchers with the opportunity to present and exchange ideas of their work. The competition's locations change each year depending on which university wins. And it is held at that university next year. Then. The challenges for the autonomous vessels change each year, and to the right here on the screen, you can see 4 different challenges for the year 2019. In 2020, because of COVID, there were no competition held. The first one in the top left is a simple race where you need to round 3 virtual buoys where the user inputs waypoints, and then you round the 3 waypoints and then go to the finish line. In the bottom left, you can see the station keeping and avoidance. This stage is about using a camera to detect a physical buoy, and then you have a virtual buoy, and then you need to circle around the buoys for a set amount of time before you can go to the finish line. The third stage is the collaborative area scan, and to the top right, where you need to go into each small square only once, and you need to visit all squares. And to the bottom right, you can see the hide and seek, which is the fourth challenge, and consists of 2 teams taking turns playing hide and seek. So the boats go from parallel from each side towards each other, and the one is hiding the April tag that is set on their sail, while the other boat is using their camera to try and detect that April tag and gather information from it and prove that they found it. Next slide. Yeah, thank you. Stint. So AutoSail is part of a Stint collaboration. And Stint is the Swedish Foundation for International Cooperation in Research and Higher Education, and was set up by the Swedish government in 1994 with the mission to internationalize Swedish higher education and research. It promotes knowledge and competence development within internationalization and invest in projects proposed by researchers, educators, and leadership at Swedish universities. It promotes internationalization as an instrument to enhance the quality of research and higher education, increase the competitiveness of universities, and strengthen the attractiveness of Swedish universities. This collaboration for the AutoSail project is between the University of Technology in Panama and the University of Antioquia in Medellin and our Mälardalen University. And at Mälardalen University, AutoSail is one of 4 current Stint projects. AutoSail will create an autonomous boat that has full autonomy, where the user inputs waypoints and the vessel calculates the path using the path planner, and then navigates to each waypoint. It will feature a simulation environment to test algorithms, object detection for buoys and APL tags, and in the future, object avoidance. The first sub-goal is to compete in the World Robotic Sailing Championship in 2021 and win. And the second sub-goal is to sail across the Atlantic Ocean. The ultimate goal for the project is to support facilities and vessels, both manual and autonomous, above and below the surface during installation, inspection, and maintenance at sea. And now Johan will talk about the dependable management in the project.
Yes, hello, can you hear me?
Yes.
Yes, so during the AutoSail project, there has been a focus on the dependability aspect. This is mainly due to the concept of the competition, which is an unmanned autonomous vessel, where there is a high need for the system to work as intended, so there would be no damage or otherwise conflict of the operation. 4 unique management roles have been active in the project to support this, where the first is a requirements manager who has set and maintained the project requirements that are based on the project goals Simon just introduced. A safety manager to analyze and provide the safety requirements for the operation of the unmanned vessel. A quality manager to uphold general quality of the project. A validation and verification manager to verify that the requirements of the project have been met throughout the process. So, first off, the requirements have been based on the following 7 areas and derived continuously throughout the project. Data logging, as there has been a large focus on the sensory system since it is an autonomous vessel, so that can be used for different things such as simulation and general optimization of the product. A diagnostic system so that the system can be assured to be working during startup since it is autonomous. Simulation to test the different software functions and the functionality of the algorithms. AI and path planning so that the vessel can be autonomously steered. Control of the rudder and sails of the vessel so that it can be controlled as per the path planning waypoints. And autonomy throughout the whole system so that it can be autonomously and unmannedly controlled. And finally, waterproofing so that no damage from water should occur to the system that we have implemented. This resulted in around 300 total requirements for the system, and it was kept in a matrix to link to different tasks and activities, so traceability and version control were kept throughout. To further showcase the requirements and make an understandable model for the different members of the project, a system model was created. This was done in System Modeling Language, or SysML, as it can be used in the open source Eclipse IDE very easily. And it looks something like this. This is an overview of the entire model, and I will showcase on the next slide what the black rectangle looks like once you further examine it. So on the right, you can see what was on the previous slide, the black rectangle area. And on the left, you see a block that showcases what the bottom square on the right looks like if you would view it internally. It is a very high abstract black box representation, but By doing this repetitively for each level, a complete view of the system can be viewed at different levels and with different information. And these 4 boxes on the left are the main areas that have been implemented, which is power supply, navigation, a safety system, and actuator control. For the safety of the project, which has been an important part due to the autonomous as previously mentioned, this is the system safety management activities that have been used. As you can see, they have followed a almost linear path throughout. Most of the activities here have been based on this matrix that shows the risk analysis performed early on. This was a way to show and identify the different risks of the system and keep them in a place where you could use them to understand what the risks of the system were and introduce the correct safety precautions. From the different safety aspects of the work, the following 4 main areas were used for safety implementation. Fuses throughout the entire electrical system, battery protection in the form of a battery management system, and a fireproof housing, as the battery was deemed the most riskful of all of the hardware components. An emergency switch that can be activated both on the vessel and remotely, so that at all points of the operation, the vessel can be turned off, even if it's acting autonomously. And water level sensors, as there's always a risk for leakage or otherwise water entering the system internally. So with these water level sensors, a pump can be activated to remove water in case of a high level detected. For the quality, this is an outtake of the front page of the AutoSail quality policy that has been used for the project. It has been something that has been part since day 1 to uphold a certain quality of the project. And it has resulted in 2 main effects on the working of the project. The first is the Plan, Do, Check, Act, or PDCA in short, which is a system that is used to standardize tasks. This to the right is a picture of how the tasks are structured in the Teams platform that we used. And by using a PDCA, you force collaboration in a way, because the plan and do part of a process is done by one individual, while the check is done by another. And then the act is done collaboratively. So in this way, there's always 2 people doing or being involved in each of the tasks that have been performed by the project, or at least 2. And this is important by the last point, that you should never verify your own work. So by doing this, a quality has been increased from all of the tasks, since you always have had at least another person involved. The second part is that reviews have been conducted on all the documents throughout the project. This is an exempt from the review protocol that is very basic at this stage. It's basically a checklist where you can see the different information that has been deemed that you should check by the quality policy. And if this project should be expanded, this should also be expanded to incorporate whatever quality goals you have set. The last part is the validation and verification, which are processes that aims to support the assessment of the requirements, both in their formulative state and their implementation. For this project, 2 different standards have been used to create processes within the project, which are the Aerospace Recommended Practices and IEEE Standards Association standards. This aims to create a large amount of documentation that can be used as evidence to if a task has been correctly implemented or if it hasn't, and what the case might be, and to link all of these without the different work in the project, so it all has a clear traceability, so you know why something has happened or why it hasn't, and also to know when something has changed. Validation has been performed on almost all hardware components to make sure that they actually they meet the demands that we ask of them. Furthermore, all of the requirements have been validated when formulated for the following 5 areas: correctness, consistency, completeness, readability, and testability. And this is to make sure that all requirements meet a certain base level. And this has created a large amount of documentation that proves or disproves this in a clear fashion that has been accessible to all members of the teams, kept in different matrices that link the different requirements or different validation activities to the correct hardware. Verification has also been performed to verify that once a requirement has been created, that it is completed, or if it isn't completed, why. The strategy for this has been to follow the standards previously mentioned and to verify all requirements at the end of the project. This has mainly been performed by different types of tests, and it has been done especially for the hardware, software, and communication. And just like validation, it has resulted in a large amount of documentation that shows the results of this that can be used for evidence to say, yes, this has been completed, or no, this has not been completed. Images and video have also been created in a large amount to provide extra evidence for this. The testing process has mostly taken place at the collaborative center, where the implementation has taken place, especially for hardware and communication, since it has been a difficult task to do a fully integrated test, since it requires you go to an actual lake or something of the similar. Software has been reviewed throughout by different forms of unit tests, and different standards has been kept to make sure that each function written meets certain standards. And a few tests have been performed with the entire system on the Lake Mälaren, where you have put everything together and done the functional systems testing at the end of the project. So yeah, now Emma will talk about the hardware.
Thank you, Johan. I will first introduce you to the vessel Norrsken, and then I will go through the system and its components. And finally, I'll talk about how it can be controlled both manually and autonomously. See if we can switch slides. Yes, now. So this is the vessel Norrsken, and it was used as platform for this project. The vessel is a 1.4 meter long, one-masted sailboat with 2 sails. It has a width of 0.4 meters, and from the bottom of the keel to the top of the mast, it reaches a height of 2.3 meters. There are 2 PWM-controlled servos on board, one for the 2 sails and one for the rudder. As can be seen here and here, we have 2 wide hatches for reaching the hull of the vessel. Through them, the components of the system can be reached. To protect the components inside the hull in case of leakage, splash-proof cases were designed and constructed. So this is the hardware system and consists of the following components. We have 2 NVIDIA Jetson TX2s, which are single board computers. The first SBC, as we call the main SBC, as we have here. It's used for calculation, handling the various control systems such as the path planner and the acquisition of data from the sensors. The second SBC, called the Vision SBC, it handles the data from the camera and image processing. The sensors implemented on the vessel are a GPS, which is used for determining the position and speed of the vessel. We have an IMU for retrieving the information of the positioning and the heading of the vessel. And we have a wireless ultrasonic wind sensor, which was installed at the top of the mast for determine the angle and speed of the wind. Finally, we have a stereo camera for buoy and April tag detection. Since the amount of PWM outputs on the SBCs are limited, a servo motor controller was implemented. The controller is capable of controlling both of the servos simultaneously. For communication between the vessel and land over 4G, a RUTX11 router was implemented. And in case of leakage or power faults, the vessel was equipped with a safety system, as we have here. It consists of water detectors, a bilge pump, and current sensors. And since the SBC handles a lot of data, a microcontroller unit was implemented to monitor the data from the water detectors and current sensors and for controlling the bilge pump. The water detectors were installed at the lowest point inside the hull together with the pump to be able to pump out water in case of leakage. The water detectors, the current sensors were implemented on the power lines for the most crucial and high power components, such as the SPCs, the router, and the motor controller. The system requires a power source that can deliver at least 12 volts and handle a current of at least 11.5 ampere. To fit the system requirements, a custom-made battery had to be designed and constructed. The constructed battery consists of 16 lithium-ion cells, which are connected 4 in series and 4 in parallel. It delivers a maximum voltage of 16.8 volts and 14,000 milliampere hours. A BMS board was implemented to make the battery safe to charge and use. The chosen BMS has several desired functionalities, such as overcharge and over-discharge protection. Since the components in the vessel require different voltages, a power distribution board was designed and constructed. It divides the output from the battery into several different power lines with different properties to be able to distribute the components with their desired power. For efficiency and robustness, manufactured DC-DC converters were implemented, as you can see here. And the DC-DC converters are highly over-dimensioned for security and safety. Fuses and diodes were also implemented for additional safety. The vessel can be controlled manually using a radio frequency controller, which communicates with a receiver inside the hull connected to the servos. Joystick 1 and 2 on the controller can we control the sail and rudder service respectively. With switch number 3, the system can be switched to sail autonomously. The switch sends the selector signal to a MUX, which forwards either the RF controller commands or the commands from the motor controller to the servos. The RF controller is set as master on the MUX, so that if the system would shut down, the RF controller would automatically have control of the servos. Also, in case of system shutdown, a smaller battery, which is not connected to the large system, was implemented for powering only the RF receiver and the servos. Switch number 4 is connected to a power switch, which cut the power from the main battery when activated. Now over to Patrick, who will talk about the software and how the vessel can be controlled autonomously.
Yes. The AutoSail vessel is powered by ROS, the robot operating system. One of ROS supported operation system is Ubuntu 18, which is installed on the vessel's computer. ROS provides a flexible structure for writing robots software with its modular and community-driven framework. Its popularity stems from how a modular system of nodes can be built and a community-driven framework. And the communication between these nodes functions. It also supports multiple programming language, which shows to be Python. The microcontroller uses its own development platform called STM32, which is based on C and C++ with simple peripheral control. Some functionality is required for the Sable to navigate autonomously between waypoints. This includes a path planner, a rudder, and sail controller, where the path planner will plan a route to a given coordinate, while the rudder and the sail controls the direction and speed of the vessel. For the external communication, a Whaler system was needed to log data from and send the path planning parameters to the vessel. Therefore, a zero-tier network was established. Zero tier allows for a private tunnel to be established from a device to another via a server, which relays the data. From this, tunnel data could be stored by utilizing the ROS bag functions in ROS, which saves all subscribed topics in a bag for later use. A secondary communication link to the system was established via the 5 GHz Wi-Fi. A 5 GHz connection was chosen due to the interference between the Bluetooth communication and the 2.4 GHz mode. A redundancy system which utilizes LoRa was planned. However, due to a change in priority, said system was not implemented. For internal communication, we can see in the figure, we can see that the devices connected to the main SBC are GPS, motor controller, EMU, LoRa, and MCU, the microcontroller. The devices were configured to always have static USB ports assigned as to not have race condition conflicts. The wind sensor utilizes Bluetooth, and while the TX2 has a built-in Bluetooth module, an external USB transceiver had to be used due to the signal strength not providing sufficient for reliable connectivity. The Ethernet communication via the 4G router was implemented to support the ROS communication between the main and Vision SBC, as well over the zero-tier network, which, as explained earlier, allowed for sending of path planner parameters and remote data logging. The map gathers all the data from the following sensors: currents, water detectors, and battery, and send them with the help from a serial communication and via USART at a baud rate of 52 kilobit per second. 3 of the current sensors work on I2C protocol, while the 4th communicates via an ADC. The water detector sensors were read as digital, while the battery was read with the help from the ADC. These values are published on the ROS network to allow for visual monitoring on our end. Besides sending data, the microcontroller also controls the bilge pump to power on when both water detectors get wet and power off when they are not wet. 2 water level detectors was also implemented, which worked on the microcontroller and used the ADC DMA, but they were discarded due to their unstable accuracy. This is the water sensor bilge pump that were used. A control system adjusts the input to a process in order to achieve a desired output of the same process. One of the simplest methods of system control is by usage of a PID controller. The AutoSail vessel uses 2 separate control systems, one for the sail and one for the rudder. I will begin by explaining the sail control. The purpose of the sail on the vessel is to create a force driving the vessel forward. When an incorrect angle is used, the wind will not move along the surface of the sail and therefore not generate any lift. When the wind comes to the side of the vessel, it will begin to roll. Because of this, a PD controller was implemented to counter the roll by releasing the sails. The integral part of the PID controller is omitted since the apparent wind direction is constantly changing. As such, there is no optimal value to reach. The rudder controller is also a PID controller that has either course or heading as inputs. The reason for switching between inputs was to counter the drift occurrence. When there is a strong wind, it will cause the vessel to rotate, and the course that the vessel is moving on will not align with the heading of the vessel. Therefore, the course of the vessel is used, meaning the direction the vessel is traveling. The course is computed by a coordinate from a global navigation satellite system. This, however, causes problems at low velocities, as the precision of the navigation system will make it difficult to determine the course. Therefore, the heading of the vessel is used at low velocities. Now, Casper will talk about the path planner.
Thank you. The path planning algorithm used in this project is called potential field algorithm. The algorithm considers the environment as a potential field with attractive and repulsive forces, and the vessel as a particle, which can be affected by these forces. The attractive forces emanate from a waypoint or a goal, the current waypoint, and are pulling the vessel towards it. The repulsive forces emanate from obstacles and are pushing the vessel away from it. Since a sailing boat cannot sail directly against the wind, these no-go zones over here are also added as repulsive forces. So here's an example of one of these profiles, a potential profile or the environment. Darker colors are represented as lower potential, and lighter colors are represented as higher potentials. So in this figure, you can see that this darker spot here is the current goal. We have 3 obstacles over here. This one is kind of hard to see. And we also have the no-go zones represented over here. Each point in the profile is calculated relative its position to the goal, to the obstacles, and to the wind. This is the equation used for calculating the goal potential. It's the Euclidean distance from the point to the goal. And there's also a scalar weight, which determines how much the goal is going to affect the environment. This is the equation used for calculating the obstacle potential. And basically what it does is it increases the potential the closer the point gets to the obstacle. You also have this d-inf, which is the distance of influence, which is a limit for how big an area the obstacle will affect the environment. After the potential profile has been calculated, the side angle is calculated, and that is you extract the lowest point in the profile, which is over here, and you take the angle from the midpoint, which is the position of the vessel, to this point, and then you get the desired course. After you get the desired course, the potential profile is calculated anew, and the new desired course is calculated. This slide shows the equation used for the potential relative wind. So first you have this one, which is if the point is inside the no-go zone, meaning the current point we're calculating is inside one of these zones, then it gets a set value of potential no-go zone, which is a high value. If the point and the heading is in the same direction, meaning the heading is over here and the point is in this side, this zone, basically on this side of the no-go zones, then this equation is used. It basically calculates how large part of the current velocity is of the maximum possible velocity. And there's also a scalar weight. If, however, the point and the heading are in opposite direction, as is shown in this zone, the same calculations as previously is made. However, extra pH is also added, which is the potential hysteresis cost. And this is done to control tacking. So if a waypoint was over here and we're trying to travel towards it, then we're going to travel along this no-go zone. But when the vessel goes below this line, then this zone over here is going to be closer to the waypoint and therefore have a lower potential, and therefore the vessel is going to try to tack over here. The higher the potential hysteresis you have, the further the vessel can travel along this line before tacking over the no-go zone. Then, after you have calculated all these three potentials for a single point, they are summarized, and that becomes the overall potential for that single point. This is speed polar diagram, which is used to calculate this Vmax and also the limits of the no-go zones. So here you can see that you can extract the possible velocity in each direction and also the limits for where you can travel. To generate the speed polar diagram, you need extensive data about the physicality of the vessel, or you have to do a lot of testing in a real environment and see the behavior of the sailing boat. Therefore, we chose to use an already existing diagram created for another vessel. The speed polar diagram uses the true wind of the environment. And since the wind sensor is on top of the mast, it is also going to be influenced by the velocity of the vessel itself. As you can see over here, this is the apparent wind, which is the measured wind. And if you then use this equation along with the velocity of the vessel, you can extract the true wind. This is a potential profile at a point of time extracted from one of our simulations. As you can see, a radius has been added around the vessel. Otherwise, there would be a bias towards the corners. So if, for example, a waypoint was over here, then since this distance is longer towards this corner, you're going to get points here that are closer to the waypoints, meaning it's going to get a bias towards the corners. You can also see that a heading has been added. This is just for illustration purposes. And as you can see, this zone over here has a much higher potential, and that is partly due to the hysteresis cost. It is also partly due to the fact that it's further away from the waypoint. This is a comparison of the hysteresis potentials. So the environment in both these pictures are exactly the same. The x's are obstacles, and this point over here is the goal, and this is the starting position. The wind is coming from this direction with a 45-degree angle. As you can see, a hysteresis cost of 1 means that you're going to tack a lot more than a hysteresis cost of 15. This is generated in a perfect environment also, meaning that it shows only how the path planner would plan the route and is not using a controller or is affected by the waves or drift. So this is a perfect environment and it's not actually true environment. As you can see, the angle at which the vessel travels when tacking is going to be the same, no matter how much hysteresis cost you have. So this angle, which is the same for all these, is also the same as this angle, meaning the velocity when you travel over here is going to be the same as when you travel over here. The distance is also exactly the same, meaning the only difference between these two in the time it takes to perform this configuration is the time it takes for the vessel to perform a tack. Therefore, if the space allows for it, you want a hysteresis cost that is high enough as to only tack once. We also implemented a functionality for the vessel to circle waypoints within the potential field framework. So temporary waypoints are created around the original waypoint. And if this is the vessel, then it's going to find the closest waypoint, which is this one, and then just go from one waypoint to another until the time has gone out. This has not been tested in a real environment. However, it has been tested in the gazebo environment, and that indicated that the implementation was performing correctly and the vessel was able to circle the waypoint. Now it is Patrick who will continue.
The vision goals are taken from the competitive events. As mentioned earlier, we have to circle a buoy, which is inside an area. To do this, we must first detect the buoy. Another event was about detecting April tags on another vessel at a certain distance. To detect this buoy, the open source OpenCV is used. We created a color mask to detect the color orange. It generates a black and white image where the white is the orange color of the buoy. With this, we can detect the contours on the mask and extract the middle point of the object and save it as X and Y coordinates. The distance to the object are known because we have the Z camera. It has stereo vision, which can create a point cloud. Now we have the distance to every point in the cloud and can extract distance to the object and publish the object position to the ROS network. And to detect the April tags, we use the April Tag 3 library with a ROS wrapper or ROS support. This library can detect different families types, but for simplicity, we chose to detect one type of family. When a tag has been detected, we send information to ROS network, including the ID, orientation, and distance to the target tag. And to simulate a sailboat, both wind and water physics are necessary to affect the lift and drag of the vessel. We use an already existing open source project to simulate a sailboat with both wind and water physics built in. The open source simulation boat called RS750 that we use to simulate our controllers due to the lack of drag and lift coefficients for our vessel. Some aspects of the physical model were disregarded, such as where the sensor were placed exactly and the boxes containing the sensors. This resulted in a different weight distribution and where the data is originally gathered. Various other tools were used to monitor the simulation, such as RQT, RWiz, and MapWiz. RQT were used to monitor and dynamically reconfigure the system in runtime. RWiz displays how the sail and rudder position according to the vessel, while MapWiz is a tool to place coordinates onto Google Maps to generate waypoints for the path planner. Here's the video on the real test. Here we used MapWiz and we placed 3 waypoints where it should be heading to. This is a result of one of our real environment tests. We placed 5 waypoints in a numerical order, which the vessel had to follow. The wind is the direction of the arrow. Because of this, the vessel had to perform tacking when ongoing to waypoint 3, as seen in the figure. The vessel started close to the first waypoint here, and have to sail to the second waypoint right here. As we can see, when the vessel reached waypoint 1, it experienced a drift and went in an arc towards the second one. And this may due to the low velocity and the controller not switching. After waypoint 3, the test after reaching waypoints, on the way to waypoint 3, the vessel had to perform tags, as we can see here. And after reaching waypoint 3, the test got interrupted due to the weather condition and the lack of wind we had. So this is the final result and discussion for the project. The lift and drag coefficients were unknown since we lacked the required tools and data sheet of the vessel to retrieve them. This caused several important optimal variables to be unknown, such as angle of attack, sail of the angle, and speed polar plot. This results in an unknown maximum speed of the vessel. With this, the set sail angle to the wind direction was probably not the most optimal. A PID controller was used to control the sail and rudder due to its simplicity. But due to the nonlinear forces acting upon the input signal caused by natural forces, a more sophisticated controller that could predict waves to correct the heading before it is altered is preferred. The Pathfinder could successfully navigate a series of waypoints. The figure represents the simulation tests. It started at the lower left half and has a waypoint at the top right with a southwest wind direction. This means that the sailboat is going upwind and has to perform tags, hence the zigzag pattern as shown. Since the hysteresis was constant, it decided to perform tags more quickly the closer to the waypoint it was. Therefore, a dynamic hysteresis would be better since it could change the hysteresis depending on the distance to the waypoint. One important aspect to note is that the wind speed and direction in the simulation are constant with some noise, while in a real environment it constantly changes. The sail controller could not be tested properly in the real environment since the rope to trim the sails were constantly getting tangled. We were unable to determine the cause and had to therefore set the sails in a fixed position about halfway full trim to continue this testing. The switch on the RF controller functioned properly to switch between manual and automatic control of the vessel at any time. Due to these integration issues with the system, test could be performed. So the future work for the project: in the next iteration of this project, a re-evaluation of the requirements must be made. With this, our evaluation of the safety verification and validation must also occur. The software could be improved by implementing an object avoidance system with the object detection. This could be integrated on top of potential field due to its flexible nature. Proper lift and drag coefficient for the vessel used must be extracted to achieve optimal speed. The hardware is to avoid getting the ropes for the sails tangled. A rope weave solution could be applied, which would solve the biggest hardware problem that emerged during the project. The cases used inside the hull were splash-proof. However, custom-made EP67 rated cases will be preferred in case of leakage. And this is all for us, and thank you very much.